The physical state of the Arctic Ocean in winter 2026 is defined by a loss of structural integrity. The ice sheet is fracturing from within. For 2 consecutive years, the winter sea ice extent has stalled at 14.29 million square kilometers. 2025 and 2026 now tie for the absolute lowest winter maximums ever recorded in the 48-year satellite history. To understand why the winter recovery failed, we have to evaluate view heights in 3 dimensions. NASA's ICESat-2 mission uses precise laser altimetry to calculate exact surface height, measuring the structural thickness of the ice pack, rather than just surface area. This map visualizes ICESat-2 monthly gridded thickness data across the Arctic basin between 2020 and 2025. The magenta zones highlight the oldest ice, measuring over 5 meters thick. Over this 5-year window, those zones are almost entirely eradicated. Since the 1980s, 95% of multi-year ice has been destroyed, leaving a vast layer of thin, seasonal ice. These consecutive record lows demonstrate that the Arctic has lost its thermodynamic capacity to rebuild structural ice during the long, cold winter months. For decades, standard large ensemble climate models operated on a core assumption regarding internal decadal variability, the natural cyclical fluctuations of the Earth's climate system. These predictive models projected that natural internal variance was responsible for driving up to 50% of the accelerating Arctic sea ice loss. This assumption carried significant policy implications. It suggested the existence of a natural buffer within the climate system, implying that a large portion of the melt was a reversible natural cycle that could eventually swing back and absorb external heating. However, new statistical analyses relying on historical satellite observations suggest a different ratio, questioning whether that natural buffer is as significant as the models assumed. To calculate the actual sensitivity of the Arctic to anthropogenic forcing, we have to move past predictive model assumptions and interrogate the raw empirical data. Researchers analyzed the complete 1979 to 2021 satellite record using a specific analytical framework called low-frequency component analysis, or LFCA. The primary objective of LFCA is to mathematically separate long-term anthropogenic forcing from the shorter-term variations of internal climate variability. The process begins by building a covariance matrix, combining 3 major datasets into a single grid: summer sea ice concentration, 500 hectopascal geopotential height, and global annual mean sea surface temperatures. The first mathematical filtering step applies a 10-year Lanczos filter across this raw data grid. This filter strips away high-frequency interannual spikes and short-term weather anomalies from the dataset. What remains are isolated low-frequency patterns, or LFPs, mapped through empirical orthogonal functions. These patterns are derived entirely from actual satellite observations, circumventing the built-in biases and assumptions of predictive modeling. By isolating these components, LFCA identifies specific spatial patterns that evolve on decadal timescales, separating the influence of external warming from the background climate noise. Applying this analysis reveals one dominant pattern in the data: low-frequency pattern 1. This dual-pane graphic charts the footprint of LFP1. Spatially, it covers the Pan-Arctic region, and temporally, it maps a downward trend in ice cover across 4 decades. LFP1 is the forced response, driven directly by anthropogenic greenhouse gas emissions and rising global ocean heat. This single forced pattern accounts for approximately 90% of the low-frequency variance in Pan-Arctic sea ice area over the satellite era. It dictates the long-term trends in the Arctic's most vulnerable regions, specifically driving the decline in the Barents and Kara seas. The data suggests that the collapse of the Arctic sea ice over the last 40 years is an irreversible, externally forced response, not a transient phase of a natural cycle. Internal variability, represented by LFP2 and LFP3, does exist in the data, but its influence is highly specific and regional. LFP2 represents atmospheric circulation anomalies. It isolates events like extreme high geopotential pressure systems becoming trapped over the central Arctic. This chart highlights the historical footprint of LFP2. During the melt period between 2000 and 2012, internal atmospheric variability accelerated summer sea ice loss by approximately 30%, compounding the 50% forced decline. We can contrast the dominant, forced pan-Arctic trend with regional behaviors governed primarily by this internal noise. The Bering Sea is the primary outlier. Here, decadal sea ice trends are completely dominated by the third pattern, LFP3. The behavior of the Bering Sea is tightly linked to natural oceanic cycles, specifically the Pacific Decadal Oscillation and variations in the Aleutian low-pressure system. While internal variability drives localized anomalies and can compound short-term summer melts, it accounts for only a small fraction of the underlying 40-year pan-Arctic decline. When the results of the LFCA are applied to the full 1979 to 2021 observational record, a consistent metric emerges. Over 4 decades, internal decadal variability accounts for less than 10% of total Arctic sea ice loss. This visual compares the historical model predictions against the observed reality. The assumed 50% natural buffer shrinks to a 10% sliver. This correction implies that Arctic sea ice is structurally more sensitive to external anthropogenic heat than previously published literature suggested. This brings us back to the record winter lows of 2025 and 2026. The failure of the winter recovery is not a product of bad weather or internal variance. It is the physical manifestation of the LFP1 forced response. Because 95% of the thick multi-year ice has been eradicated, the system has lost its thermodynamic resilience to external forcing. The mathematical safety net we believed was protecting the Arctic does not exist. Now that the Arctic can no longer rebuild its thick winter shield, compounding physical mechanisms are triggered across the basin. This cross-section illustrates a consequence of this missing ice, Atlantification. Warm, dense Atlantic water is now pushing northward, intruding deeply beneath the fragile surface ice. This influx destroys the ocean's stratification. Deep thermal energy is pulled upward, melting the surface ice from the bottom up. Without the protective layer of multi-year ice reflecting solar radiation back into space, the externally forced warming loop becomes self-sustaining. The stakes extend far beyond the polar circle. The destruction of the Arctic's thermal regulation alters global weather patterns, disrupts international trade routes, and impacts ecological security. Empirical observation indicates the internal variability buffer is small. Global risk models must be recalibrated for an unavoidable, externally forced, ice-free Arctic reality.